In this video, we will learn about polarization of light. We have already mentioned that light is a transverse wave of electric and magnetic field, with the electric field perpendicular to the magnetic field. And the direction of the electric field is called the direction of polarization. We can produce electromagnetic waves that are polarized in a certain direction. And for example, we can do this using an antenna. So the electromagnetic waves emitted by an antenna are polarized. And this is because the electrons oscillate along the direction of the antenna rod, so vertically in this picture. And so the electric field is also vertical. On the other hand, if you look at light waves emitted from a light bulb or from the sun, those are unpolarized because the electrons or the atoms are moving in random directions. We can also polarize light using a polarizer. A polarizer is a material that will absorb one of the polarization components. So let's say that you have unpolarized light going through a polarizer. The light is unpolarized, so it contains many different polarization components. And if the polarizer has a vertical polarizing axis, then it will absorb the light that is polarized horizontally. And so the transmitted light will be polarized in the vertical direction. The most common type of polarizer is a Polaroid, which is a brand name for a dichroic material, and that material absorbs light differently depending on the polarization axis. Now, the first results that we will show about polarization is that the intensity of unpolarized light is reduced by half after going through a polarizer. So I polarized is equal to 1/2 of I unpolarized. Now let's first look at the unpolarized light. The intensity is proportional to the square of the amplitude of the electric field, and the electric field is unpolarized, so it has all kinds of directions, which we can decompose into two components, right? One where the electric field is parallel to the polarizing axis, and one where the electric field is perpendicular to the polarizing axis. And so because these two components are perpendicular to each other, then their scalar product is 0. And so we simply have that the intensity is proportional to the sum of the square of the two components. Now, let's look at the intensity after going through the polarizer. The perpendicular component has been absorbed, and so the intensity is proportional to the square of the parallel component only. So now, if we consider the two intensities, why would the polarized intensity be half of the unpolarized intensity? In fact, for the unpolarized light, on average, there will be the same amount of parallel and perpendicular components. And so this way you see that the contribution of those components to the intensity will be the same. And so you see that the intensity for polarized light is half of the intensity for the unpolarized light. Now, what happens if light that is already polarized goes through a second polarizer? In this case, often the second polarizer is also called an analyzer. So now you have the light that is already polarized along a certain direction, and it goes through the analyzer. So the final intensity after the analyzer will depend on the angle between the polarization axis of the incident light and the polarizing axis of the analyzer. Again, you can decompose the electric field of the incident light into a component that is parallel to the analyzer axis and a component that is perpendicular. Right? The parallel component will be E0 cosine phi, and the perpendicular component will be E0 sine phi. But the perpendicular component will be absorbed by the analyzer, and so the intensity is proportional to the square of the parallel component only. And so the intensity will be equal to I max times cosine square of phi. And this is known as Malus's law. In fact, Etienne Louis Malus was a French scientist who discovered this law, and his name is actually written on the Eiffel Tower. So if one day you visit the Eiffel Tower, then remember Physics 9b, Malus's law. Every year, more than 7 million people go to the Eiffel Tower, I believe, in honor of Malus's law. So that tells you how important is this law, right? Now, if you go there to the Eiffel Tower, maybe you will be wearing sunglasses, right? And some sunglasses are polarizing, right? How can you check? Well, you need two pair of glasses, and if they are aligned, the angle phi between them is 0, and so the intensity is maximum. But if they are 90 degrees from each other, then the intensity will be 0, and you won't see anything. And if you only have one pair, you can also check with your computer screen, right? Because the light from your computer screen is also polarized. Now, if you think you understand polarization, then watch this. Okay, if you're confused right now, this is a good sign that your brain is functioning properly, right? This is not obvious at all. So let's look at what happens. The light from the screen is polarized. So we consider a polarizer number 1, that is in the screen. Now, if there is another polarizer with a polarizing axis that is perpendicular to the polarization axis of the light, then after going through this polarizer, then the intensity will be 0, right? This is just simply the definition of what a polarizer does. But if we add another polarizer in between, and the polarizing axis is 45 degrees from the polarizer number 1 and number 2, then what will be the intensity just after this intermediate polarizer? According to Malus's law, it will be I naught cosine square of the angle between polarizer number 1 and polarizer number 3. So cosine square of pi over 4, which is also you can simplify as I0 over 2. Now, what will be the final intensity after going through polarizer number 1, 3, and 2? Now, the light has a polarization axis that is 45 degrees from the polarizing axis of polarizer number 2. And so I2 will be equal to the intensity just before, which is I1, times cosine square of the angle between the incident light and the polarizer number 2. So cosine square of pi over 4. Again, you can simplify this as I1 over 2. And since I1 is I0 over 2, then I2 is I0 over 4. So you see that I2 is not 0, even though the first polarizer of the screen and the last polarizer number 2, are 90 degrees from each other. But what matters is the angle between the polarization axis just before the polarizer and the axis of the polarizer itself, right? So it does not matter what the polarization at the very beginning was. So only just before the polarizer. So when you have such a problem with several polarizers, then always remember to apply Malus's law to each polarizer one by one, right? Don't skip a step.